Okay. So today we'll have a short class till 5. So today we are going to talk about a different problem, the problem of like forecasting of the Indian monsoon. So like as you know, the Indian monsoon is the phenomena of the standard rainy season, which causes rainfall from roughly from June to September for 4 months. I mean, that is the prime rainy season for most parts of India, except some parts like, say, the eastern Tamil Nadu coast and like there are other places. Like basically, southeastern India, it receives retreating monsoon rainfall in October and November also. But the vast majority of the Indian landmass receives most of its annual rainfall during the monsoon season of June to September. And needless to say, like much of the economic and agricultural activities also depend on this monsoon because most of the crops are dependent on rainfall for the irrigation. So the Indian rainfall is like it is an extremely important thing for India, and hence it is also necessary to forecast it in advance. But the thing is that is we like sometimes we hear things like this year monsoon is expected to be above normal, or this year monsoon is expected to be below normal, and things like that. So these forecasts are made by Indian Meteorological Department, the IMD. So what they try to do is they consider external factors, the climatic conditions all over the world, and based on that, they try to predict how much rainfall is going to happen in India during the monsoon season. So these they can do because it is known that the Indian monsoon is dependent or is affected by climatic conditions in various parts of the world. I mean, not only around the Indian region, but also like at quite far off places, like say, as far as say the Pacific Ocean and the Atlantic Ocean. So there are the Indian Meteorological Department. They had a series like they have various statistical model. There are some 8 parameter models, 16 parameter models, etc. I mean nowadays they do it in a different way. But earlier, like they had a set of parameters or if you call it a set of predictors from different parts of the world, which tried to based on which they tried to make the forecast. Now the aim of this paper is to identify the various predictors of Indian monsoon using the data. Like earlier, they like the different predictors they used was like based on their understanding of the physics of the climatic system, which of course was limited in various ways. Now the aim is to use like machine learning to identify which other climatic factors from various parts of the world can be suitable for prediction of Indian monsoon. So this paper, this was like it came out in 2016, and these two persons were from IIT Kharagpur itself. So Professor Pavitra Mitro, some of you may even know, he's a faculty in computer science and engineering department. And this person, Professor Ravi Nanjundia, he is one of the most famous climate scientists in India. Like he's from Indian Institute of Science, Bangalore, and he was also the director of Indian Institute of Tropical Meteorology, which is like one of the biggest research institutes in India that deals with climate and weather prediction. So let us so let us go over this paper. So first, look, let's go through the abstract. Prediction of Indian summer monsoon uses a number of climatic variables that are historically known to provide a high skill. However, relationships between predictors and predictant could be complex and also change over time. The present work attempts to use a machine learning technique to identify new predictors for forecasting the Indian monsoon. A neural network based nonlinear dimensionality reduction technique, namely the sparse autoencoder, is used for this purpose. It extracts a number of new predictors that have prediction skills higher than the existing one. Two nonlinear ensemble prediction models of regression tree and backed decision tree are designed with identified monsoon predictors and are shown to be superior in terms of prediction accuracy. So, basically the idea is that they will use this or like autoencoder, the sparse autoencoder. So we'll show how exactly that sparse autoencoder is used. So using that sparse autoencoder, it will extract and it will basically they will have a large number, very large pool of predictors. That is, they will measure different variables at or different climatic variables at different parts of the world and throw all of them as inputs to the model and then see which of them are useful for the prediction. So they will try to make it as sparse as possible. That is, so that sparsity. So we'll try to understand how that is done, and then which a small that way like from that large number of potential predictors, a small number of predictors will be selected. And what they have shown is that many of these predictors which they select using this process are actually quite new. That is, they have not been used earlier, or they have not been known to be useful for monsoon prediction earlier. And one using those, once they have identified those predictors, they will do the actual prediction of Indian monsoon using two non-linear ensemble prediction methods, namely regression tree and back decision tree. So I hope those of you, like all of you, have studied machine learning and you have idea about what these regression tree and decision tree these things are. So, like, these are pretty straightforward machine learning models, or I mean predictive models. So we'll come to it later. So the proposed model shows a mean absolute error of 4.5% in predicting the Indian summer monsoon rainfall. Lastly, the geographical distribution of the new monsoon predictors and their characteristics are also discussed. So first, let us understand what this machine learning method called autoencoder, what it is. So this is what the autoencoder it looks like. So let us say you have a set of input variables. So the input variables are like x1, x2, x3, x4, x5, etc. And so these are the inputs. Now what the autoencoder does is that it creates a just like in any neural network, there are these hidden variable. So these hidden variables actually calculate some complex function involving the input like parameter, like various input variables. And there can be multiple hidden layers like that. In this figure only one hidden layer is shown, but in reality there can be multiple hidden layers. Now, in case of autoencoder, what happens is that like progressively the number of nodes keeps on decreasing. That is, let us say the input has n, like there are n input variables. Then in the first hidden layer, there may be half that number. Let us say n by 2 variables. In the next layer, there might be n by 4 variables, etc. Till they reach some one layer called the bottleneck layer, which is the smallest. Let us say it has only some like 5 variables or something like that. Or this is suggesting, this figure is suggesting, let us say there are only 3 variables in the bottleneck layer. And after that, it again keeps increasing the number in the subsequent hidden layers. Again, it keeps increasing. And finally, in the output layer, we have the same size as the input layer. So if the input layer had n nodes, the output layer will also have n nodes. And the idea is that the autoencoder will be able to exactly recreate the input. That is, whatever is the input is being passed, the same output, the output will be the same as the input. So that is why it is called as auto encoder. The auto indicates that it's the same thing. Like it gives the same, it's an encoding of the thing itself. It's not that it will take in some input and produce something else, but it's like the input itself will, like they will create a this representation of it. So then you might wonder that if the input and output are the same, then what is even the purpose of doing all this? I mean, what is the hidden layers actually doing? So what the hidden layers are doing is that they are, as the name suggests, they are encoding the things. So as I said, the input layer has n nodes. The first hidden layer may have n by 2 nodes. So basically these n by 2 nodes, what it does is it forms a code for all the like the information that is here in the provided as the input. So they will like combine the different inputs and calculate some kind of function and store it there. So that will be like a code of size n by 2, and then further operations like that will be carried out so that we get a small a code which is even smaller and so on. Finally, we reach the bottleneck layer, which is like the smallest code or the most dense code. It's like that is your input may be of size n, but the code is like of size only say 3 or 5 or something like that. And then so like when you study machine learning, you may have come across dimensionality reduction, principal component analysis, and things like that. So you can so like in a sense here also something like that is happening. The input data is you can say is n dimensional, but it is being represented in a three-dimensional way. Now the those three dimensions, they may be some linear or non-linear combination of the different inputs. Okay. So now, just like reduce in case of PCA, once we have the reduced like low dimensional representation, that can be utilized for various classification and other things. So this small thing, this small representation, that it will be used for the like they may use that for the like whatever analysis they want to do. Now this is about autoencoder. Now is in general. So now let us see what they want to do with the autoencoder. So identification of monsoon predictor using autoencoder. So let us see. So first of all, let's consider the input variable. So as I said, their aim is to predict the monsoon rainfall over India. So for that, they need to consider like so like they will they start with a huge pool of potential predictors. So there are essentially three categories of climatic variables: the air temperature, the sea surface temperature, and the sea level pressure. So air temperature is something which is measured over land. The other two things are measured over the oceans. So it's like everywhere, all over the world, they will like the world, all the land regions that can be divided into these into grids. The way we have always considered a grid structure on like on the region of our study. So at each grid point over the lands, they will consider the air temperature. So like if the entire world like all the entire land all over the world, let us say it is divided into some 10,000 grid points or so based on latitudes or longitudes, etc. So at each of those grid points, this air temperature is measured. So like basically we have 10,000 readings of those air temperature. Then similarly, sea surface temperature, like that is, let us say all the entire sea region or the ocean region all over the world. Let us say it is, we again consider these grid boxes over or grid points over there. So let us say there are another 20,000 points, and at each 20,000 of them, they have measured the sea surface temperature as well as the sea level pressure. So 10,000 from here and maybe 20,000 from here, another 20,000 from here. So total 50,000 possible predictors might be there. Of course, the actual number used in this study is not so much, not like 50,000 or anything like that. So what they have done is they have like considered very big, very large grids. That is the each that is there are 20 the each grids is of size 20-degree longitude by 10-degree latitude, right? uh, So like as you can understand, so usually we can for these climate purposes we consider 1 degree by 1 degree or quarter degree by quarter degree grids. And like while we are studying the remote sensing satellite case, we are talking about say 50 meters and so on for every pixel. So here it's like it's much wider, it's like 20-degree longitudes by 10-degree latitude. So like that almost means like 1000 kilometers, and that is each side of the pixel is of the size of say of the length of say 1000 kilometers or 2000 kilometers. So basically they have divided the world into very large groups of areas, so that way they have got only 324 grids. Okay, and as a pre-processing steps, the grids having less than 20% values as null. So like I mean, there are like whenever they you measure any particular values, there like in case of climatic data. So those of you who are like some of you may have come across this problem in your assignment 2 or the projects also. So there are null values, like a particular variable may not be defined at all positions. So those null values, so those grids which contain too many of these null or nan values, they are just dropped. So like after pre-processing, the number of input nodes in the autoencoder for so like basically what they do is they build three autoencoders like this. So like as I said, there are three categories of climatic variables: air temperature, surface temperature, and sea level. Sorry, sea surface temperature and sea level pressure. So they have three autoencoders for this purpose. Now, the first autoencoder, the one for air temperature, that has 136 like input size of 136, which basically means that it is the input is the air temperature at 136 regions over the world. Uh, like they are all regions over the over the land. Okay. Now, similarly, for the sea surface temperature, this is 137, and for sea level pressure, it is 102. Okay. So now what they do is that they will, so the monsoon, the next step is monsoon predictor identification. That is, they will like utilize these autoencoders to identify which of these things, or I mean, which of these these inputs which they are measuring, they might be useful for monsoon prediction. So first of all, what they do is as follows: they do something like a dimensional reduction. That is 137, 136, 102. These many inputs are there. They first want to reduce the dimensions. So what they do is as follows. So this is one particular approach which they have followed in their paper. I mean, there are other ways also of approaching the same problem. Like in fact, if some of you want to do this project, you could have I think like you do it in a different way. So this is just to give you an idea of how they have done it. So separate autoencoders are designed for all three climatic variables. As I said, there are three autoencoders. We use single layer autoencoder for our approach. So like immediately the question might have arise. So this paper was written in 2016, say 6 years earlier. So at that time, like the idea of deep learning had still not was not maybe that much popular as it is now. So they had used a single layer autoencoder, but nowadays people use deep autoencoders with a large number of hidden layers. Like this is one aspect which like if any of you want to try this out, this like the first improvement you can consider is instead of single layer autoencoder, you can consider multiple layers. Now, input layer consists of nodes corresponding to the climate variables of selected grid points. Input to hidden layer ratio is some 15%. So basically, this is the number. So whatever is the number of input variables, the hidden like the number of hidden variables will be the 15% of that. Those 15% of the node, so 15% of 136 is let us say it is something like 20 or something like that. So those so the bottleneck layer which I mentioned, so there are it will have like this, it will have say 20 nodes. So so it's you can consider it as a 136 dimensional data reduced to 20 dimensions. The nodes in the hidden layer represent the composite features which are represented by the potential predictors. Composite features, why? Because the each node is basically it's a non-linear combination of the various inputs. So that is why they are calling as composite features. Now now what is done is that the input is, so like now they train the autoencoder. The autoencoder is trained in the sense that like they have data. So from this period 1901 to 1993, so these 93 years of data, and in each of those the 12 months of those 93 years they have observations. Observations means observations of air temperature at all those 136 locations, observations of the sea level pressures at all those 102 regions and so on. So, and the total number of data points is this 1116, correct? So like in every case the input is the same as the output. So what is done is that like using all these observations, the aim is to learn the weights of the different edges of the autoencoder. So each of these edges from the hidden layer to the I mean from the input layer to the hidden layer, as well as from the hidden layer to the output layer, each of these edges they have some weights, as well as there are some other parameters. So the values of all these weights and parameters are like estimated by solving and some kind of an optimization problem, uh, so that the in every case in all these 1116 like I mean 1016 cases, the input variables and the output variables are almost the same, or are as close as possible. So that way, what like they get the weights of all the edges. Now once they have got all the edge weights, what they do is they threshold the weights. So those weights which are like let us say which are lower than a threshold, they are like those corresponding features are just dropped. Like they are considered to be as not important. So let's see what they are saying. After the autoencoder being trained using using the training instances, post processing is performed to obtain the new predictors. We examine the weight matrix corresponding to the input to hidden layer. For each hidden node that represents a potential predictor, we divide the range of weight into 10 equal intervals and plot the frequency of weight in each interval. So these 20 things, that the 20 nodes which they are considering, so each node is basically a linear, like represents a non-linear combination of the different inputs, right? Because like the nonlinear combination is achieved with the help of these edge weights as well as whatever activation function they are using. So I mean the nonlinearity is enforced by the by that activation function, and the each of these hidden nodes, they are like like they are dependent on the different input variables. Now so what they will do is, or what they plan to do is, they want to rather than considering these inputs as potential predictors, they will use these hidden nodes as the potential predictors. I mean, that is when they do the monsoon prediction, they will not consider these huge set of inputs for prediction predictive purposes. They will use with a small number of these hidden layers, each of which is basically a combination, is some function of the inputs as the predictors. So that way they achieve two things. First of all, the number of predictors they need to consider for monsoon is not much. There is the number of inputs may be very high, but the number of outputs is, I mean, sorry, the number of hidden layers is like pretty small, say 15, 20, etc. Right? So and that way it becomes easier to hand the data that or the prediction problem becomes easier to handle. And then each of these hidden layers, they are actually a like some kind of function of the inputs themselves. Each of these is is a separate function of the inputs. So it's like the information from the input that is anyway encoded in this small number of hidden nodes. Fine. So after the autoencoder being trained using the okay, so what they do is now they consider the edge weights which are attached to these hidden nodes, and then they identify those edge weights which are like small. So let us say xi represents input node and hj represents the hidden node. Okay, so n is the number of inputs, which is something like 130, and j is the sorry, m is the number of hidden nodes, which is like say 10 or 50, or sorry, 15 or 20. And wij represents the weight of the edge connecting xi with hj. Okay. Now, so these weights are they have been learned by solving that optimization problem. So for that, of course, like training algorithms are there, which gives you the weights. So now, what they are saying is, so the value stored in the hidden node hj can be expressed in this way. Now, so what they will do is they will like drop off all the input nodes for which the connection to the jth hidden node is below the threshold. So let us say come here. So so if we write like this, let us say this weight is 0.5. Similarly, just a second. So this one, so this is just saying that the strength from the influence of the first predictor on the first hidden node is might be 0.5. If you consider this one, so let us say this edge weight is 1.9. This edge weight is say minus 0.03. This edge weight is 12.7, etc. So now, what these numbers suggest is that this x4 has a very important contribution on h1, while these ones x1, x2, x3, etc., they have only very marginal contribution on h1. I mean, h1 is basically is equal to some activation function times the this kind of thing, where I is the inputs. So now some like if these some of these weights are very small, that is close to zero compared to the others, so that will mean that those particular inputs are not playing much role or much are not influencing these hidden variables much. Fine. So, so like what they do is for the like for simplification of the whole representation, they just pretend that those things are not even there. So that way, each one will be considered in this case to be a function of only x4, but probably not of x1, x2, and x3, and so on. So this way, like each of those hidden nodes now is considered as a like a nonlinear combination of only some a small number of these inputs. Now, now how to choose that threshold? That is for that they have used some criteria to choose the threshold on the edge weights. So now that they have got those things, I mean those hidden variables, they call as the composite variables or the composite inputs. So each, let us say that the first hidden variable h1, let us say it is a like a combination of let us say feature of x4, x9, x 17 and x like 86. Then might so that is to say only these weights are significant, the weights to all other inputs are 0. Let's say h2, that may be a combination of say x12, x 23 and x 34, etc. So and their remaining are all zeros. So that way, each of these hidden variables, like these are in a sense they are the composite variables. So what they will now do is that they will use the values of these composite variables to predict Indian monsoon. So as you can see, they have data for they mentioned these 93 years and 12 months. So, now in each of those 93 years, the Indian summer monsoon has one particular value. That is the net rainfall like over India in that particular year during the monsoon season. That is June to September. So that's a particular number. So the aim is using like in any given year or in a, that given these kinds of value, I mean given the values of these different composite features, can you predict the Indian monsoon? So they frame it as some kind of a regression problem. The input is the values of these so-called composite features. The output is the Indian monsoon. And the composite features, remember that they are coming from three different autoencoders. The first autoencoder is for the air temperature, the second autoencoder is for sea surface temperature, and the third autoencoder is for sea level pressure. So let us say the first autoencoder has like say some 15 composite features of air temperature. The second one has some 10 features of or 10 composite features of sea level, sea surface temperature, and so on. So total they have about 50 composite features, or say maybe 40 composite features of the different variables. So they will use these 40 new features to make the prediction of the Indian monsoon, which is a single number. So for that they will use these machine learning algorithms like this regression tree or the weighted decision tree or whatever, yeah, bagged decision tree, etc. So these are like ensemble machine learning methods, which I guess most of you know. So we'll not go into the details of that. So like the decision tree is as you as you know anyway, like it uses a subset of the features to take decisions, and then it makes the final prediction. So now if instead of having a single decision tree like that, what if we have an ensemble of decision tree? That is ensemble as in like let us say each tree is trained on let us say a subset of the features. That is, instead of all the 40 odd predictors, let us say each tree is focuses only on a randomly chosen say 12 features or something like that. Now using those 12 features it will try to make a prediction. Next let us consider another tree that again takes a like subset of say 21 features or something, and use them to make the prediction, etc. So this way we get a collection, or as they say an ensemble of trees, each of which makes a prediction, and then they somehow calculate the mean of those prediction as the final prediction. So that is what they have done, and they get some kind of a like some kind of a prediction, and then what they do is they calculate the error. That is error as in like in every given year there is the actual let us say year number T, the Tth year, there is the actual Indian rainfall, which is often referred to as ISMR. Like it basically means the Indian summer monsoon rainfall, that is the aggregate rainfall over India. So this quantity is there, which is obtained from measurements, let us say by the India Meteorological Department or something. And then there is the WYT prime, which is basically the prediction given by these regression trees based on those composite prediction terms. So now there will be an error. The usual, it might be the usual mean square error, say, yeah. And then this error is can be measured in the different years. And so like as you can see, they have considered like, so they are showing that is they can use the various number of I mean they can use a certain number of years for training and the rest of the years for testing and so on. So they find that as they increase the training number of training years, this error initially decreases till a particular point. After that it keeps on increasing. Why does it keeps on increasing? Due to overfitting. That is, it like it overfits on the training data set and is not able to do the like testing. I mean, on the test years, it is not able to do the forecast well. So they find that like if they use about 25 years for training, that way they get the best error. And that and the errors are the error using the regression tree is slightly better than the error using the ensemble of these decision trees. So, so yeah, so once that is done, so once they get the predictions, okay, so first of all, they are able to make up in any given year, they are able to make a prediction of the Indian monsoon. And as and one thing to be noted is that these various variables which they were considering, they are that is the air temperature, sea surface temperature, etc. Those variables are measured in different months. And so Indian rain monsoon is from June to September of every year, but they can measure those variables in, say, let us say January, February also. So if they find that using the variables of like of different climatic I mean the different climatic variables in January or February, if they are able to predict the Indian monsoon rainfall for that particular year, that is very useful, because that means they are able to make a very that is ahead of time they are able to make a prediction. That is already in say February or March, they are able to predict whether how much rainfall is going to happen in this particular year and so on. And then of course they will be able to like if that can be forecast accurately, then people will know beforehand that is there this year will there be excess rainfall or deficient rainfall, so they can make preparations accordingly. So, so that is one thing. Now the other aspect is what about the predictors? So that is actually the more important aim of of this paper. That is, rather than forecasting the amount of rainfall itself, what they are trying to do is they are actually trying to identify like what are the variables which are helping in the prediction. So, so like those in the world map here, they have actually tried to show the those things, those variables. So, so like as you can see, this is here we are looking at considering the air temperature in specific. So, the different, so these are so like as I was telling, the each of those hidden or composite variables which they have considered, each composite variable or each hidden node is like a like combination or nonlinear combination of the inputs from different parts of the world. So the importance of those inputs can also vary. So let us say, what they're trying to show is that, let us say 81. Okay, so the blue indicates the let us say the first hidden variable, the first predictor. So let us say the first the first composite variable that is that comprises of or that is a combination of the air temperature from different parts of the world, namely this part which is blue and also this part which is blue. So as you can see, this is something in the in South America, and this is the air temperature somewhere in the let's say, let us say, around Cuba or something like that. So that is the first composite variable is a, you can say, is a combination of the air temperatures in South America and Cuba. That forms the first predictor for Indian monsoon. The second predictor, this green, this is something which is observed in like the with it covers these grids as well as these grids. That is grids again near in the around Cuba in the Atlantic Ocean, and two more grids in Europe. So the second composite feature, it includes air temperature from some parts of the Atlantic Ocean and also some parts of Europe. The third feature again, the this purple color. So you can see that the purple color is present here. So basically it means that the third feature, the third composite feature is is depends on the air temperature in the Pacific Ocean as well as in South America and stuff like that. Okay. So this is the this is how it works. Now if we so this is about the air temperature. Now if we come to the sea surface temperature, there also we see something like the same thing. So again, there are they have considered six of those composite features. The first composite feature, blue, that is a function of these grids, and these grids. So there are six input grids, like two of them in the Indian Ocean and four of them in the Pacific Ocean. Then there is the second composite feature, which covers these green grids, which are like two locations around around South America, two around the African coast, and two more around, say, Australia, New Zealand. So it's a the second is a composite of these things and so on. So similarly for the third one, which is a sea level pressure, they will have some like you can see these kinds of composites. So the curious thing here is that the different features which they are considering, they are spread all over the world. That is, this composite feature, like part of it is in the Pacific Ocean, and part of it is in the Indian Ocean. For the second one, part of it is near America, and part of it is near New Zealand, and part of it is also near Africa. So like the geographical diversity of each of these composite features, that is very large. So now, of course, use identifying these kinds of predictors using machine learning is one thing, but then the question is, do these predictors actually make sense? That is, is there actually any scientific or any physical reason why the let us say the sea surface temperature in the Indian Ocean or in the Pacific Ocean, or the air temperature in Europe and parts of Africa, or in Japan, why these things will play a role on impacting Indian monsoon? So that is an open question for climate scientists to find out. Uh, so this Professor Ravi Nanjundia, who is one of the authors of this paper, actually investigated all these predictors and tried to come up with some explanation about why by what mechanism, by what physical mechanism these variables can influence the Indian monsoon. Some of those explanations are given in this paper itself. So that is what that is in these later papers. And now if we come to the prediction skill of this model, so now let us see what is the performance of the different features by themselves. I mean, That is by features I meant that these air temperature, sea surface temperature, and sea level pressures. So if you consider only the air temperature, nothing else, not the other things, then what is the error they get in the different cases? Or if with only using sea surface temperature, what error they get? So these kinds of things also they have studied. And then so here what they have they are comparing the actual versus the prediction. So the in the for the years from 1901 to 1993, these 93 years they have used for training their model, and the remaining years, say 1993 to 2014, the next 20 years, they have used for the testing, that is for validating of the predictions. So you can see that in each of the years, so let us say in 94, this much is the actual rainfall, and the prediction which they have made is which they have been able to do is like something like this. And then in the various other years also, you can see the prediction versus the actual amount. So you can see that there are some years in which there is a big gap between the potential, I mean the actual rainfall and the predicted rainfall. But in most years, they are actually quite close. So like, for example, if you see this year, 2006, they are almost identical. Or this year, 2013, again, they are quite identical. In these years, say 2000, 2001, 99, the prediction is very close to the reality. And 2002, this is a drought here, like this year, that is there was very little rainfall, but and most of the models which Indian Meteorological Department was using at that time had not been able to predict this drought. So that is they were at that time, of course, this work was not done, but in 2002. But when this drought happened, people were caught unawares, because no model had been able to predict that there would be a drought. But you can see that this model, it is actually predicting maybe not so much, but still low rainfall. It's relatively low rainfall that year compared to other years. So if this model had been there at that time, maybe like people would have been more that is, they would have been warned beforehand that a drought is going to come. However, in another important drought year at that time was 2009. This drought was even worse than 2002. But this time, unfortunately, the model by this paper was not able to predict it. So, like here, you can see that although only this much rainfall happened, the model had predicted this amount of rainfall. Now, the reason for this is again that this year 2009, this was a very special year in which certain like there was a cyclone called Ayla in the Bay of Bengal, which is considered to have absorbed a lot of moisture, which and as a result of which the rainfall was less that year. I mean, the cyclone had come just at the onset of the monsoon, and it had uh, like carried away much of the moisture, and as a result of that, the monsoon rainfall was relatively less in that year. But uh, this model, of course, is does not take that factor into account. It tries to make the predictions only using the air temperature, sea surface temperature, and sea level pressure. So, what the model is suggesting here is that had that cyclone not happened, then this year it would have been, the monsoon would have been more or less normal. And so yeah, so these kinds of studies, the further they have done these kinds of studies about if they had used only the air temperature, or if they had used only the sea surface temperature, only the sea level pressure, etc., then in what in then how the predictions would have been, and so on. So it turns out that in most of the cases, if they had used only one of the predictors, then maybe the predictions would not have been that great. Like for example, here in this year 1994, there was like this bar indicates that there was actually a significant rainfall. That is, this zero here does not mean zero rainfall, but it indicates the rainfall anomaly. So anomaly is a concept we are familiar with. That is the overall value of, I mean, that is the observation minus the long-term value. So anomaly 0 means just the long-term value. So in this particular year, 1994, there is, like you can say, there was a, we can say it's a 10% anomaly. That is the increase, or the anomaly that happened is actually like a very significant 10% of the annual, or the long of the climatological value. But these so we can call this 1994 as some kind of an excess rainfall year, where there was so much of excess rainfall, but none of the variables by themselves alone had been able to predict it. That is, the prediction using the sea surface temperature, that is this pink diamond, and the prediction by air temperature, the star, the blue star, they actually indicate slightly below normal rainfall this year, while sea level pressure indicates only slightly above normal. While the fact is there was a huge excess of rainfall. But now if you consider all the factors together, now we can see that, I mean, okay, this year the prediction was still not great. That is, there was a big gap between the actual rainfall value and what was predicted. In subsequent years, you can again see that if you are considering only a single predictor, then we are not being able to do particularly well. But that's what this figure suggests. But if you look at this figure, you would see that in most cases, if we consider all the predictors, then then you may be able to do better, and so on. So yeah, so that kind of, basically that kind of study they have done, and here they have actually made the comparison with the different models that which are used by India Meteorological Department. So like India Meteorological Department at that time had various models called, I mean, they also had their own sets of predictors. They had some eight predictor models, some 10 predictor models, 16 predictor model, and so on. So here they have compared the error of forecasting by the IMD models as well against the forecasting by their models. Even if they have considered the three factors: air temperature, sea surface temperature, and sea level pressure separately. And here they are showing that in all the cases, they are able to get better results, that is lower error of forecasting, than the existing India Meteorological Department models. So that way, this paper is quite significant, because it shows that using this machine learning technique, it is actually able to identify a very novel set of predictors of Indian monsoon, so which are indicated by these maps. And most of these predictors, I mean, were not known to climate scientists earlier. That is, climate scientists may not have known that the sea level pressure near Japan, or maybe the sea surface temperature around Florida, these things also play a role in influencing Indian monsoon. These things may not have been known to climate scientists earlier, and they are also showing that if you use these predictors, then you will be able to make a better forecast of Indian monsoon rainfall than what was possible otherwise. So that is what this paper is about. Now, this paper came out in 2016, but if you look at now, turn back at this paper, you can see that there are many obvious scopes for improvement. So first of all, if you consider, there is no need to that is the study which they have done here is quite restrictive in a number of ways. So first of all, we did not need to restrict ourselves to only one hidden layer. We could have considered like many more hidden layers also. And we could have considered different nonlinear activation functions like TANH and all those things, as they do in case of deep learning. And that maybe that way, we like the composite variables which we would get, they may be more complex and also more representative than the composite variables which they have got. And besides the inputs which they have considered, that is, they are considered like those are like very coarse grained. So that is, as I said, they are considering 20-degree longitude by 10-degree longitude. That is, if you consider each of these grid boxes in these maps, so these are like like 10-degree latitudes by 10-degree latitudes, means like say 1,000 kilometer by 1,000 kilometers. Yes, so usually 1 degree is roughly corresponding to 100 kilometers. So 10 degree will mean like 1,000 kilometers. So each of these like so 1,000 kilometer by 1,000 kilometer region, they are approximating by only one number. So they may be like throwing away a lot of information there. So that is not a great idea, especially now that we have high resolution data as well as more computing power. So we do not really need to restrict ourselves to say 130 input variables or something like that. We can do with say 10,000 input variables also we can handle now. So these are some of the obvious ways in which this paper can be improved upon. Then finally, the prediction which they have made, the prediction of the Indian rainfall, that is done using these regression trees. But it might be possible to use other models also to make the prediction. And finally, most importantly, they what these guys predict is a single number as the Indian rainfall. That is the aggregate Indian rainfall, like aggregate rainfall over the Indian landmass in any given year. But what we want is a special distribution. So instead of giving predicting the special aggregate, maybe like at if they could predict at different locations, that would have been useful. And is in fact some of their subsequent works try to do that. So these are some ways in which they can this paper can be improved upon now, and some of